Um, okay, so let's see. What's I could do? I could do a joke to get you quiet, but I forgot all my jokes. Okay, so maybe this is not appropriate, but if it's inappropriate, please don't. It is inappropriate. Okay. So I saw this on TV. It was an inspirational story. And it was an 80-year-old grandmother who told the joke. So, from Montana. What's the joke? I'm Satish Rao, by the way. I'm the one who's co-teaching with Christos. So the joke is there's this captain of a ship, and there's a person in the crow's nest, and the person in the crow's nest calls down and says, "Oh, enemy ship approaching." So he tells his cabin boy to, go down and give me a red shirt. And so the cabin boy gives him a red shirt and comes up, and then they have a battle and they win. And then the cabin boy asks him, "Well, why did you want a red shirt, Captain?" And the captain says, because in case I get injured and I bleed on my red shirt, the crew doesn't see that I'm bleeding, and they don't lose heart, and they don't lose their courage. Okay, so they go on sailing, and then a guy from the crow's nest calls down and says, "Captain, I see 10 enemy ships approaching." And the captain tells the cabin boy, "Okay, you need to get me my brown pants." Okay. All right, so do I have your attention? All right. Okay, so account forms you could have them now or after class. Yeah, I have my white shirt. So, okay. Problem sets due tomorrow at 6 o'clock, okay? So try to get all your technical issues dealt with. In particular, account forms are here. And by the way, you see all this text on here? Those are instructions, okay? So you can try them, and if you can't do them, don't be shy. The worst thing to do is to not ask for help. If you don't get in your account and you have a problem, I might say RTFM, but I will help you, okay? So is that clear? So I don't want any excuses. Last semester I taught a course, and during finals week, somebody came up and asked me how to use the account. So it was really I wasn't very happy about that. So while I might be annoyed if you ask me stupid questions, I'll be really annoyed if you don't actually get what you need done. Okay, that's really my job, is to help you get what you need done. Okay. So lecture 3. We're going to go over this. Christos started this last week, so we're going to do a bunch of stuff. We'll see how much we get through. Okay, so multiplication. 2 n-bit numbers. There's x and y and some sort of funny figure that I represent. Like the box is supposed to represent an n-bit number, and the twice as long box is representing a 2 n-bit number. Right? The product is going to be longer than the original number. Right? Okay. So now let's think about the kth bit, how we compute the kth bit of xy. Okay? So I'm going to denote the ith bit of x by x sub I, and the ith bit of y by y sub I. So really the kth bit of x times y is you multiply the ith bit of y times the k minus ith bit of y. I mean, the ith bit of x and the k minus ith bit of y, and you sum it up for every possible combination here. Okay? So this is something, that's just what multiplication is, right? You have the 5th bit of y and the 8th bit of x. When you multiply those bits together, that actually is representing what happens in the 13th bit, the 8 plus 5th bit, right? That's going to be that power. Okay? Okay, so the number of basic operations in this is the definition of multiplication, right? So even in the definition, how many operations are there? Well, to compute the kth bit, you have to do k multiplications, more or less. This is k, but it's a little bit more complicated for these high bits. You don't have to do very many multiplications to get the most significant bit. But more or less, you need to compute k products. Okay? So now if you think about this, for k equals 1, this is 1, plus 2, plus 3, plus 4, plus 5, plus 6, up to n. Right? The sum of I from 1 to n is n squared over 2 approximately, right? So that's theta of n squared. So even the definition of multiplication, sort of when you write it down, has an n squared in it, right? So it's like, it's kind of a nasty operation. Okay, so you have these nice numbers, n bits, 2 n bits numbers. Your output is only 2 n bits, but the work to get it is n squared. Okay? Okay. Yeah.
Are these slides going to be available online on the website?
Maybe. No, they will be.
It's actually easier to listen to rather than.
No, of course. They'll be on the website. I'm just kidding. Okay, so they'll be on the website. Yeah. So yeah. Okay. So they'll be on Piazza. Okay, I'll post a thread. It's pinned. There's a certain rhyme and reason to Piazza. We're going to pin important threads on the top, and they'll always be on the top. And you guys can actually pin a thread too with the pound pin, and I can undo it if I feel like it shouldn't be pinned. So okay, so I sometimes fix some of your language too. Just no offense, but okay. So although after that opening joke, it seems I have no right to do so. Okay, so you can think of this, we're going to break it down. We're going to do a recursive algorithm because we're computer scientists. We like recursion. We're going to think of the top n over 2 bits as x sub l, and this is what Christos did last lecture. X sub l and the low order n over 2 bits is x sub r, right? It's just how it's written. Okay, so x sub l is n over 2 bits, and x sub r is n over 2 bits. The value of this number is 2 to the n over 2 times x sub l plus x sub r. Okay? Okay. So now y sub l, same thing. We can write y sub l that way. Okay, now when we're going to multiply it out, now we're going to think about multiplying this thing out. So x times y is this times this, right? We're just substituting math. Okay, there's some FOIL thing you do, first, outside, inside, last, and you get this, right? When you multiply the first, you get this times this, which gives you a 2 to the n over 2 times 2 to the n over 2. You get a 2 to the n, and then you get xl and yl. Okay? And so on. The reason there's 4 terms is first, outside, inside, last, right? Is everybody okay? 4 products. Okay. So there's 4 n over 2 bit numbers here, multiplications. X sub l times y sub l, x sub l times y sub r, and so on. Right? Does everybody see those 4 n over 2? There's also these multiplications, but I'm not worried about these multiplications because what? You just shift it to the left. You shift to the left. Okay, unlike the rest of the country. Sorry. So you shift to the left. I mean, or it's impossible to do in Berkeley to shift to the left, but you do it here anyway. So I got to make jokes on both sides of the political spectrum. And Berkeley is such an easy target. Okay, so anyway, so you shift to the left, right? 2 to the n is just taking your numbers and padding it out with 0 and moving it to the left. That's linear time. So we're not worried about that. This addition is just addition. That's linear time. We're not worried about that, right? The multiplications, they're brutal. It's hard to do. It's hard to multiply. Okay? So we have this recurrence. T of n equals 4 t of n over 2 plus O of n. This is our snazzy new recurrence. This is our snazzy new recursive algorithm from multiplication. It just rocks. And it really does. It's sort of nice for a lot of reasons, and we'll get into that later in terms of parallel, in terms of how computer architecture works. For large numbers, this is actually a better algorithm than the naive algorithm. Okay? But what is it in terms of asymptotics? It's not so much better. It's theta of n squared. Okay, so y is the solution of this recurrence, theta of n squared. We'll do that in a few slides. I'll show you how to solve such recurrences. But for now, trust me, it is theta of n squared, so it's not so great. Okay? How did we attain the bound? Yeah, we'll do that in a few minutes. Okay? Okay, so do people understand this algorithm? It's actually pretty straightforward. Okay? Yeah. Yeah, and then what I'm going to do is I'm going to recurse. This is a recursion. So my program, my computer program will take my x. It's just a recursive program. It says there's n bits. I'll divide the x, I'll divide the y, and then I'll do a recursive call to do this one, and a recursive call to do this one. Okay? And a recursive call to do that. That's a good question. Okay, and a recursive call to do this one, and a recursive call to do this one. So now I want to analyze the runtime of my algorithm. And my algorithm does the same thing, right? So to do this n by n bit multiply, that's t of n. What we're going to do is 4 recursive calls, 4, right? 1, 2, 3, 4. And now the size of the numbers in each one of these recursive calls is what? N over 2. So that's this argument. Okay? Plus O of n. O of n is there to do the addition. Afterwards, after you're done with the recursive call, you'll get your answers here. You'll get this answer, this answer, this answer, and this answer, each of which will be n bits. And you add them together and shift them and do whatever you need to do as described by this program, by this expression, and then you move on. Okay? So this recurrence comes from this algorithm, which is a recursive algorithm, which means you call the algorithm itself on different inputs which have smaller size. Okay? Okay, so so in a moment I'll show you some code. Okay, so now Gauss's trick, right? This Gauss is everywhere. He's amazing. Okay, he's amazing. He has one of 4 laws in electricity and magnetism. On and on and on. Everywhere you go, there's Gauss. And so here's one of his tricks. Okay, so AC. So I'm just multiplying complex numbers. Again, it's kind of FOIL, right? So there's going to be 4 products: A times C, A times DI, which is here, right? A times DI. I guess that's outside. Okay, inside is BI times C. You know, I'm in and inside. What's last? Last is B times D. Now the BI times DI gets you a -1, right? I squared is -1. So you get this minus BD. Okay, so you have 4. Again, you can implement this with 4 multiplications. Okay? So let's just drop the I. Let's just say we're not very smart, so we just accidentally drop the I. And we multiply these 2 together. So now we get 4 terms. That's pretty cool, right? We did, how many multiplications do we have to do here to compute this? Well, if we drop the I, we can actually just add A plus B. That's easy, right? And we can just add C plus D. That's easy. Now we just have 2 numbers, and we multiply them together, and we kind of get these 4 numbers multiplied together, right? So we did a little, just adding these numbers together really made a lot of things multiply each other. On the one hand, FOIL is bad because here you have to deal with all these things being multiplied together. On the other hand, in the reverse, looking at it the other way, you add up all these numbers and you multiply them together. Now you're multiplying all the numbers here against all the numbers here, right? So you got all these things, but that's not what you wanted. You don't want all these things added up. You don't have the numbers separately. You have them all added up, just munged together. What a mess. Okay? So we get 4 multiplications. There's the 1 multiplication, and we get these 4 objects sort of all added up, but all added up. Okay? So now let's do 2 more multiplications, which is we're going to multiply A times C and B times D. Okay? Okay, so now what we need is we don't actually need A times C. We don't actually need A times D. We need A times D plus B times C. Right? We don't care what A times D is or B times C is. We just need to know their sum to compute this complex number. Okay? So first of all, this thing is easy to compute from P2 and P3, right? You could just do AC minus BD. So now you've computed this part of the complex number. And, oh, this should be AC AD plus BC. Okay, so, okay, so now P1 minus P2 minus P3 is equal to, let's see, AC plus AD plus BC plus BD, okay? That's what P1 equals, right? We have P1. Then we subtract P3, which means we get rid of BD. Okay, and we also subtract P2, which means we get rid of AC. So we have AD times plus BC. That's what this sum equals. Okay, so we also have this. From this, we get P1 minus P3, and P1 minus P2 minus P3 is this. Okay? I'll even fix the slides before I post them. How about that? So, okay, so there you go. So Gauss figured out how to do this thing that on the face of it, the definition looks like you need 4 multiplies. You need to multiply A times C and B times D and A times D plus B times C. But he noticed, in fact, all you really need is these sums. So you only really need 2 terms here. And you can form those 2 terms out of 3 multiplies. Okay? So that's what he observed. So he got some efficiency out of it. He got efficiency out of the fact that if you just add up a bunch of things and start multiplying by each other, you really are getting a lot of things multiplying each other. Okay. So now let's look at a faster algorithm for multiplication. So again, y is equal to this. We're going to split it up. It's going to be recursive again. So y is of this form. X is of this form. Y is of this form. X times y is this thing we had before. So I need 3 terms here, right? Gauss, and for complex numbers, I only needed 2, the coefficient, the real coefficient, and the imaginary coefficient. Here I need 3. I need the coefficient of 2 to the n, the coefficient of 2 to the n over 2, and this coefficient. Okay? But I used 4 n over 2 bit multiplications to get it in the recursive algorithm. I did this one, this one, this one, and this one. Okay? So now I'm going to compute this product. I'm going to add up XL plus XR, YL plus YR. And I get some, set of things that I get out of it. Okay, again, this is 1 multiplication. Okay, now I need 2 more. P2 is equal to XL times YL, and P3 is XR times YR. Okay, so now this is the middle term. I want to compute this. So that is equal to P1, that's this, minus P2 minus P3, right? Because minus P2 takes off this, minus P3 takes off this. So we get this middle, the cross terms, right? P1 minus P2 minus P3 gives us the cross terms. Okay? So, and then we have, and P2 was this one, and P3 was this one. So we got all 3 terms. Okay? So now we have a recursive algorithm where what we need to do recursively is compute P1, P2, and P3. And more or less, again, both these numbers are n over 2 bit numbers. These are n over 2 bit numbers. And these are almost n over 2 bit numbers. They might be n over 2 plus 1, right? When you add 2 k-bit numbers, you may get a k plus 1 bit number, right? Okay, so I'm not worried about, I'm just going to go ahead and say my subprogram, instead of getting an n over 2 plus 1 bit number, it's actually getting an n over 2 bit number for now. Okay? But, okay, so this is the recurrence now. So this is better. Where we had a 4, now we have a 3. Doesn't seem like such a big deal, right? But we actually get this bound on the running time. Okay, this is a little ugly, so we can write it out this way. The key is 1.58 is less than 2, right? We were having n squared, and now we're having n to the 1.58. Okay? So that's a lot better. I mean, do you remember grinding through multiplication in grade school? Wasn't it horrible? And there's a better way, right? I mean, it's shocking, in fact, that there's a better way. Okay? And it's better. It's really better. It's a lot better. I really love it. Oh, my God. Okay, so this is this technicality that I have to deal with, okay? Okay, so is it a lot better? I don't know. Is it, let's see. Okay. Okay, so this is going to be a little tricky because I'm going to try to do Emacs looking over my shoulder. Okay. Okay, so this is multiplying. You'll get a lot out of this if you choose to learn from life. You get a lot out of every day. Okay, so you'll get a lot out of this demonstration in some sense. So you'll see the notion of big. Okay, you'll see that these numbers are big. So A is something. A is some number, right? It's just some big number. It's not that big. It's just only 20 or so digits, right? Okay, so L means it's long, but it's only long. It's only a little long. Okay, now A to the 4,000. That's really long. I mean, that's big, right? You take this number and you multiply it by 4,000, the number of digits. That's how long it is. Okay, it's long. Does that make sense? Okay, so I'm going to multiply. I'm going to use Karatsuba's algorithm. Karatsuba. Okay. It took 136 milliseconds, and it's long. milliseconds, right? Okay, that's for Karatsuba. That's a lot longer. Okay, well, did you see it? 136 versus 1130, right? It's already, only with 40,000 digit numbers, we're already faster. Right? A lot faster. Okay, so let me show you something else. I hope this works. Okay, let's see. Okay, so what do you guys think it'll take? Remember, multiply took about 1,000 milliseconds. So now I doubled both sides of the number. So how long will it take? Yeah, it's going to take 4 times longer because it's n squared, right? How does n squared? If you double n, what happens? If you change n to 2n, from n squared, you get to 4n squared. So, okay, I'm keeping my fingers crossed. Please, baby, please, come on. I haven't done it, so we'll see. Oh, yeah, close enough. Okay. No, it was 1,100, so it's really good, right? So even though the constant factors, I have no idea what the, oh my God. Okay, so even though the constant factors, I have no idea, I can understand what happens when I double the size of my n. Okay? It grows as a quadratic of the size of the factor by which I'm growing it. Okay? Does that make sense? And on the other hand, if I did k multiply, Karatsuba, it was 100. So if it was growing quadratically, it should be 400 something, right? But it's growing less than quadratically, so hopefully, well, it was 130. Okay, so it should have been 130. It should have been 500. Okay, so it's 130 times 4, which is 4. You carry the 2, and then you do this. Yeah. Okay. Okay. So now let me show you something that's interesting. Okay. So this is all very good. Okay. Well, he's using 40,000. RSA uses big numbers, by the way. So this happens to some extent, but not quite this big. But this is actually an interesting algorithm in practice. Let me show you where it's used in practice. So instead of using k multiply or a multiply which I wrote, I cut and pasted and modified. Okay, anymore who writes things. So okay, so this is Python's multiply. So I could show you. Now Python is a nice language for this because it has long numbers built in. So this is Python multiply. I'm just calling their multiply. Okay? The reason I have to do it this way is just because I want to print the timing. Okay? So I'm just doing Python multiply. So what do you think it's going to take? Is it going to be the naive one, or is it going to be faster than Karatsuba? Oh. Oh. I did this at home. Oh. Okay, fair enough. Okay, sorry. Okay, well, I didn't quite do that at home. Computers don't lie. Okay. So it's faster. It's using Karatsuba. Okay? It's like a real thing. Okay? We're just not making this up, right? So, okay. So now let's see if I can get back to my slides. F5. Okay, there's faster ones, but I think Python happens to use Karatsuba. Okay, this is called Karatsuba. If you. Okay, so this is cool. So now do you believe me on this? Yay! 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 Okay, right? Okay, so okay, now let's go and remember some math. Okay, this is just to get sorted on math again. Okay, so exponents. What we're gonna do now is we're gonna prove this bound. We're going to prove this is how you bound a recurrence. Okay? Maybe, actually, should I show you the code, or I'll post the code if you want. And then you can see the recursion if you want. Okay? It's somebody's code. So a to the b to the c, what does that equal? A to the bc. Okay, which is also equal to a to the cb, which is also equal to a to the c to the b. Okay? Okay, now the definition of log. Log is the inverse of the exponent. Okay, so a equals b to the log base b of a. What does that equal? Oh, it equals. I already told you what it equals. Okay, but you see that? It's the inverse of exponents, right? That's what it means. Log base b is the inverse of b to the, right? So if you have this expression, you can replace it by a. Or you can replace a by this expression if you want to make life complicated. Okay? Okay, finally, a to the log base b of n. Okay, n is something we care about. That's usually what we use to denote the problem size. Okay? Is the same as, well, now what I did is I replaced a by something complicated. Right? I replaced a by something complicated. Okay? And now I just switch these, right? I use this first one. A to the b to the c is equal to a to the c to the b, right? So this is, I just switched the places of these two. That's what that says. Okay? And now b to the log base b of n is what? We go the other way here. It's n to the log base b of a. Okay? So if you get an expression like this, you can. I'm going to do this. I'm going to use this conversion. Okay? Okay. Okay. So now we have our recursion. This is our multiplication. I replace the cn there because sometimes when you use big O notation, I'm going to use one c and then I'm going to use the big O notation again. So there's two different constants sort of running around. So I'm making this an explicit constant. Okay. And for convenience, I'm making the time for one to be the same as this, just to not have too many constants running around. These could, for all practical purposes, just be the bigger one of the two. And these constants are, again, not important, but I just put them for a reason. Okay, so now, okay, so this was a little scary. I should have unfolded it slowly, but it took, some technical complications. Okay, so So let's just look at this. This is a recursion tree. So the first program has a problem of size n, and what you do is you do 4 calls to this is just the recursion tree of the program. So you do 4 subroutine calls to the same program. And then, so the time for this subroutine call is going to be t of n over 2. The time for this subroutine call is going to be t of n over 2. The time for this one is t of n over 2, and the time for this one is t over n over 2. Now, the t of n over 2 consists of adding up the times for these 4 plus whatever time it takes to merge. Okay? And the whatever time it takes to merge in this case is c times n. Okay? So, you know, the top level program calls 4 subproblems, which calls 16, 4 times 4 subproblems, which calls 4 times 4 times 4. The total number of subproblems at this level is going to be 4 squared, right? The total number here is 4. Each one of these has 4 children. So the total number at this level is 4 squared. Okay? The total number at level I into the tree is 4 to the I. Okay? Now, the argument here, at the top it's n. The size of the problem is n. Okay? At the second level, you've divided the problem. Each one of these has problems of half the size. So that's n over 2. Okay? And at this level, each one you divide by half again, but divide by 2 again. And you get n over 4. At the ith level, the problem size is n over 2 to the I. Okay? Once your I level's deep in your recursion, the size of the problem has been beat down to n over 2 to the I. Okay? So now the time that you spend at this level, not recursively, is c times n, because you have your numbers you're working with at that level is of size n. People ask this question on Piazza. At each point, is it the n that's at the end, or is it the n in the middle? So in recursion problem, you think about the n in the middle. Yeah. Oh, because there's 4 here. Yeah. This recursion tree comes from this particular recurrence. Okay, so we think of this recurrence as a program that makes 4 subroutine calls to the same program. Okay, so I should have showed you that with the Python thing. But there's 4 instances. I could do that, right? So there's right, 1, 2. The program here is multiply. And there's 1, 2, 3, 4 calls to multiply. And each one of these is half as big as x and y in terms of number of bits. Okay? Okay, and once I'm going to do analysis, I just encode that information into this recurrence, saying the running time of my program with n bits is equal to whatever the running time of my 4 subroutines are, plus whatever it takes to collect the results and put them together. Okay? So, okay, so then so this is the size of the problems. Okay, so now I need to say the time per problem. That's the time to put together. At the top level is c times n. At the next level, per problem, for inside of this guy, you do c, the size of the problems is n over 2, so it's c times n over 2. This is where I didn't want to use an O, because if you use O, you could think all the constants change in the O notation. The O contains a constant, same constant for every one of these invocations. Okay? And at this level, each one of these problems is working with numbers of size n over 4 in our example, and so this is c times n over 4. At level I, each one is working with problems of size n over 2 to the I. So the problem for each one is at c times n over 2 to the I. Okay, and this last column is just multiplying this and this. The number of problems is 4 to the I, and the amount of work you do per problem to merge is n over 2 to the I. Yeah? Okay, because of because in the recurrence here, right? Because every time what I do is I make a subroutine call on smaller numbers. right? The numbers were half as big in the multiplication example. But really, I'm not only talking about the multiplication example. I'm talking about this recurrence. So I'm just saying this recurrence is equal to 4 times t of n over 2. So I'm just using the argument there, which is n over 2. Okay? Okay, so he asked why is the problem size dropping by a factor of 2 every time. And that comes from this number. So the 4 comes from this number. The 2 comes from this number. Okay, and we'll see this. I'll do this 3 times. Okay? Because once you do it 3 times, that's enough. Okay? So, so this number is just this number times that number, right? 4 to the I times c times n over 2 to the I is 2 to the I times cn. It's a number of problems times the work each problem does locally, not the recursive work. This is the local work, not the recursive work. Does that make sense? So the total work is going to be the sum of all these, right? All the local work and all the procedures is going to be the total work. Okay? How deep does this tree, how deep is your love? Okay, so how deep does this tree go? Okay, once n over 2 to the I gets 1, you're bottomed out the recursion. Right? You won't make a subroutine call. There's an if statement, if n equals 1, if the number of bits equals 1, I stop and I return the answer. Okay? Okay, so when so that happens when 2 to the I equals n, right? And 2 to the I equals n, if you plug in log base 2 of n, 2 to the log base 2 of n is n, right? And then you get a 1 there. So you won't go past log base 2 of n in this recurrence. Okay, so the depth is at most log base 2n. So now we can just sort of calculate what the total work is. So so one thing we need to calculate is how many problems are there at this depth? Well, at depth d, at depth I, the number of problems is log base 2, 4 to the I. At depth log base 2n, it's 4 to the log base 2 of n. I just dropped the 2. Which is equal to 2 to the 2 log base of n, which is equal to n squared. So there's n squared problems at the leaf. What do you think those problems are when you do recursion, when you do multiplication? They're all the bits multiplying each other. That's what the problems are. Okay? So, so there's n squared. So if there's n squared subproblems, you're going to take at least n squared time, right? Because each problem, at least you have to call the darn procedure. Okay, so already this recurrence has to take at least n squared time. Okay? Okay, each problem is of size 1. Each problem takes c time, right? That's what we assumed here. T of 1 is equal to c. So the total work in just the leaves, in just the bottom levels of the recursion, like down here, are c times n squared. Okay? Total work. So the first level, now we want to add up all the levels. I only argued about the bottom level. So the first level is c times n, c times n. The second level is c times n. The second level is 2 times c times n. The third level is 4 times c times n, and so on, all the way up to c n squared. So what is this going to be theta of? Well, this is tiny compared to that one, right? And this is still tiny. And actually, if you think about the one here, it's half as much, it's half as big as that. And this one's half as big as that. So this one dominates. This within a constant factor actually tells you the whole sum. So it's theta of n squared, O of n squared. Okay? Remember 1 plus 1/2 plus 1/4 plus 1/8 plus, what does that add up to? It's always less than 2. Okay? So that's what happens here. You get this plus half as big, plus half that as big, plus half of that, all the way down to something small. Okay, so this is why the recurrence was n squared. Okay, so now let's do this one. Okay, so here again. Okay, so now the difference here is there's a 3 here. So it's the same picture as before, except where I had a 4, I have a 3. Okay, so there's a 3. The number of subproblems at the top level is 3. The number of subproblems at the next level is 3 squared. On the other hand, this 2 is the same, so this column stays the same. It's every time you divide the problem size by 2. So And this work is, then I just plug in, right? The work is the same because it's C times n, the work per problem. Now, when you take this product, this number is different, so you get somewhat of a different result. Okay. Before, this number was 4 over 2 to the I, right? And the 4 to the I came from here, over 2 to the I came from here. Now it's 3 over 2 to the I, okay? It doesn't reduce like 4 over 2 to the I. Okay, so again, you bottom out the recurrence at the same place. The depth is still log base 2 of n, right? Because this number, the size of the problems is decreasing in the same fashion. Okay, so the total number of leaves is 3 to the log base 2 of n. This is why I did the logarithmic warm-up. It's the same as n to the log base 2 of 3. Okay, size 1, work per problem C log base n to the log base 2 of 3. Yeah, so the other one has the same form. It's n to the log base 2 of 4, which is bigger, right? Log base 2 of 4 is 2, and that's n squared. So really, this complicated expression was there before. It just happens to simplify. Log base 2 of 4 is 2, so that's why it was n squared before. It's exactly the same analysis. It just looks ugly because it doesn't sort of drop out. And again, you get a geometric sum. This problem, each one of these terms is growing by a factor of 3/2 every time. So only the last one really tells you within a constant factor what the whole sum is. Okay, which is O of n to the log base 2 of 3. Okay? Okay, yeah. Oh, it's just, okay, this is the size of the subproblem. At 1, you don't recurse. Okay, here, let me. See, it says, well, whatever the cutoff is, right? That cutoff would be 1. You don't call a recursive thing. So these will both be 1-bit numbers. So it's fast to multiply them. You don't do recursion. Once you do that, the recursion tree stops. Okay. 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 So now let's do it in general. So this was a lot of work. Every time I do a recurrence, you're going to make me draw out a tree and do this stuff. It's like it's a little bit of a grind. So I'm going to encapsulate the argument and then give you a theorem that you can apply. Okay? So basically, it's exactly the same argument, right? Where I had 4, I have A, and I put A's in all these places. Where I had 2, I put B. There's B, and I put B in all these places. Okay, this should not have a D. Okay, and now what I'm going to do is I'm going to allow you to not just add O of n, but add O of n to the D. Okay, so you may have something where the work at each stage is n squared or n cubed, right? Or n to the 1/2. Okay, so it's allowing you to fit more different algorithms. So this is a general form for recursive algorithms. The general form is you divide the problem into B subproblems, into A subproblems, each of size n over B. Okay, and it's just the same thing. Now the degree of this tree, instead of being 4 or 3, it's now A. Okay, and the size of these problems, instead of being n over 2 at half the size of the previous one, it's a factor B smaller. Okay, so and this D factor is just the fact that at each level maybe you do more work or less work depending on what this D is. Yeah. No, these are just constants. Yeah, whatever your algorithm is. We'll see it. We'll apply this thing to a few other cases. Okay. Okay, so this is the same problem. So now we can calculate all the work in terms of these variables. Where we use 4 and 3, we can just use A and B. 4 and 2, we use A and B. And we have this additional variable D, which is the exponent there. So now again, now what's your problem size at I levels? It's no longer n over 2 to the I. It's n over B to the I. Okay. Now when I equals log base B of n, you get b to the log base b of n, which gets you an n here again. Right? You get an n over n, yeah. Yeah, this should not have d's here. Yeah, these should not have d's. So this one should have a d. This one, yeah, it should not have a d. So I'll fix it. Okay. So so now the problem size at this level is n over b to the I. Once you plug in log to the b of n, right, you get n. B to the log base b of n is n, and you get n over n equals 1. So the recursion bottoms out. We always assume once you get down to problem size of 1, you don't recurse anymore, right? That makes sense. We're not real number people, right? Once you get to the smallest integer, you're done. Smallest natural number, other than 0. Okay. So the depth here is k. Again, the depth of this recurrence is log base b of n. Okay. So we have to add up all these terms up to this depth to see what our total work is. Because this is the work at this level, this is the work at that level, so we need to add up all the work at all the levels, and that gives us our bound. Okay? So let's do that. So the depth is log base b of n. The level I work is this expression. A over b. I dropped the constant c because it doesn't matter. Okay? So a over b to the d to the I times n over d, n to the d. Okay, so now the total is I just sum over all values of I from 0, 1 to log base b of n. Okay? So I get this expression. So n to the d factors out. So this is just some expression. It's a sum of this thing. What does it look like? Does it have a pattern? Each subsequent term is different from the previous term by what? By a factor of a over b to the d. It's a geometric sum, right? Again, just like the other two, it's a geometric sum. Okay, so it's a geometric series. Well, it's a geometric series inside the sum, and so we know that if a over b to d is less than 1, what really tells you the most about the sum? Well, the first term within a constant factor. Okay, so if it's less than 1, the first term, this is to the 0 essentially, right? So it's just O of n to the d. Okay? On the other hand, if this factor you're multiplying by is bigger than 1 every time, the last term dominates. And we saw before, the last term is how many leaves do you have? Well, you have b to the log base b of n. No, you have a to the log base b of n. And so this is the same as n to the log base b of a. This is just a number of subproblems. We saw it before for the recursive matrix multiplication. It was n to the log base 2 of 4. For the Karatsuba algorithm, it was n to the log base b is 2 again, and a was 3. Okay? Now, if on the other hand, every one of these terms is the same, all the terms in this sum are the same, right? If a over b to the d is equal to 1. In that case, then all the terms are the same, so you just multiply the first term times the number of terms, and the number of terms will log base b. Right? So this is the number of terms here, the depth. Okay? So this lets you solve any recurrence of this form. Okay? So there's three numbers that are given, a, b, and d. And basically, if d is bigger than this value, so this value, when a over b to the d is less than 1, you can manipulate that and see that that's the same as d is greater than log base b of a. Okay, so I just do this translation here, and I put it in a table. So this is the running time. This tells you upper bounds on the running on these kinds of recurrences. You're given a recurrence, you figure out what a, b, and d are, and you can figure out an upper bound on the running time. Okay? Okay, it's in your book, by the way. All this is in your book. So let's get this recurrence. What's a? What's b? What's D? Okay. Did I get it right? Okay, good. So D equals to 1, and it's less than 2, which is equal to log base 2 of 4, which is equal to log base B of A. Okay? Which implies that what we're saying is D is less than log base B of A. We're in this case, so we get T of n is equal to n log base B of A. So T of n is equal to n log base B of A. B again is 2, A is 4, so you get O of n squared. Yeah. Yeah, this should have an equal sign right here. Yeah. Right. Okay. Okay, so yeah. So, okay, so what about this one? Okay, what's A? What's A here? Yeah. What's B is 2 and D is 1 again. Okay? So now I'm just plugging in for A or B, and then I get a less than here. And there again, I read off the less than. T of n is equal to O of n here. Okay, end of the, did I do this wrong? Okay, so what happens here? So D is 1. Log base 2 of 1 is 0. So I get that D is greater than log base B of A. I get this case, right? So then I get T of n is equal to O of n to the D, which is O of n here. So this should be the other way. Okay, so now here, what's A? What's B? And what's D? Okay, so now 1, which is D, is equal to log base B of A, which, right, log base 2 of 2 is 1, which implies that T of n is equal to O of n times the depth, which is log n, log base 2 of n. So it's this case. Okay? Okay, so that's, that is Master's theorem. Okay, so I'm going to give you like a 2-minute break. It's probably overdue, but and then we'll continue in a minute. If people want to get their account forms in this 2 minutes. Yeah. Which one?
One is greater than log base 2.
Yeah, it should be greater than.
Oh, okay.
Yeah, it should be greater than. Yeah, I thought they mentioned it. Yeah. Okay, great. Thanks. That's it. No, that's fine. Yeah, whatever. I had enough. It wasn't a big deal. Yeah. Oh, I got to you too. Yeah. You wouldn't know where a water fountain is. Right? Yeah. Okay. Okay, so good. Okay, so one thing is that there's this issue here. Is 1 is not less than 0, so it should have been the other way, and then I chose the appropriate thing. So there's a typo here. Okay, so I promise you there will be typos. Okay, but the lectures are there's a lot of concepts in there, so don't get offended. You know, just say, okay, well, he'll deal with it. Your job is to try to not be distracted by the occasional typo. Okay, so I apologize. I'll make my job is to try to get as few as possible. But okay, so so now we're going to go on to more recursive algorithms. Now we have our fancy way. Let me get this off the slide. Okay, get that mistake out of there. So I have a board to correct mistakes. I can do derivatives. I can do the derivation again. If anybody feels that a typo is really distracting them, please just stop me and I'll do that. Okay, so the master's theorem is this theorem. We have our fancy theorem where we can do any recursive algorithm. We can basically give it a bound on. So let's go do some recursive algorithming. Okay. Okay, so let's sort the items in an n-element array. So you guys probably, who saw this in 61B, merge sort? Really? Really? Okay, who took 61B? Okay, so you didn't see merge sort? Okay, wow, I see. Okay, so there's slides with, maybe it's Hilfinger Schuchuk or something. I think Schuchuk does it, but anyway, so we're going to do it again, but we're just going to analyze it using our fancy new theorem. Okay, so we have this set of items in an array, 5, 6, 7, 9, 10, 2, 3, right? These are just objects. You know, in some sense, in general, you don't think of them as a number. You think of some object with some key that you're comparing. Okay, some big, nasty key. But here, just for illustration, we use numbers. Okay, so the merge sort is the following. So what you do is you just sort the first half of your array, the first half of your array. Now, when I say first, these are not the lowest, these are not the smallest elements, are they? When I just take the array and I hand it off to my recursive procedure, and I just give it the first n over 2 elements, is there any reason to believe that they're the smallest? No. In fact, if they were, then you'd kind of be done. Okay? You wouldn't need to sort the damn thing. Okay, so you just hand it the first half of your elements, and you say, okay, sort it recursively. And you hand the second half to the same procedure, and you say, sort it recursively. Now, if the length of A is small enough, you just return the array, because any one element is always sorted, right? Does that make sense? So a simple algorithm. Okay, so that's how you, but what you get back from these two subroutine calls is you get two sorted arrays. You don't have a single sorted array, right? You have to take these two sorted arrays and merge them, right? Does that make sense? Okay, so how would you merge them? So just think about it for a few seconds. How would you merge them? They're both sorted. I should have done it the other way, but so how do you want to merge them? Yeah. What? Right. So he said this following. Choose the lowest from the two arrays. Okay. Okay, so you cross out that one. You say, okay, well, I've already seen you, so I'm going to cross you out. Okay. And repeat. Okay, so I have the sorted subarray, 3, 7, 8, and this one, they're sorted, right? I hope they're sorted. Okay. And now I want to output things. So I have these two sorted arrays. So I pick the which one's smaller, 3 or 4? 3. So I take 3, and I cross it out, and I put 3 on the output. Okay? And now I look at it, and I'm looking at 4 and 3? No. I'm looking at 4 and 7, because I crossed out 3. Okay? So 4 and 7, which one's smaller? 4. Okay, 5 and 7? 5. 7 and 9? 8 and 9? And so on. Oh, okay, so that's it. Okay? So do people understand this algorithm? Okay. So, okay, so what's the correctness? How do you prove correctness? This is an inductive algorithm, right? So really, you just need to argue that merge works. So once you argue merge works, then by induction, you get two sorted lists. Okay, so this should be something from 70 that's pretty natural to argue for correctness. So let's see what the running time is. Okay, so the split. The first thing we do in this algorithm is we split it into two subarrays. Okay, so, you know, if you take two arrays of size n over 2, you can copy the first n over 2 to the one, and then copy n over 2 to the next. And that gives you an order n time algorithm to split. You can do it more efficiently with order 1 if you just tell the subroutine, okay, you sort this part of the array. You don't move the items. If you move the items, you're sunk. But if you don't move the items, in fact, it doesn't take any time at all to split. You just compute the middle of the array, and you hand in, okay, you sort the array, you hand to merge sort this concept where you sort this part of the array. That's what the start and finish means. So you fancy up your data structure. So this is a common thing. So once in a while, to get efficiency, what you do is you fancy up the way you call a procedure. Okay, this happens a lot. Okay, but in this case, we don't actually need the efficiency. We're just going to assume that it's order n time anyway. Okay, but I just wanted to point out there's other ways to do these things. Okay, so now the merge procedure, what did it do? It looked at each element once. It looked at each element, and if it looked at it, and then it crossed it out. It actually looked at it more than once, but every time it looked at two elements, it crossed out one. So that's the way it needs to be fixed here. But every time it looks at two elements, it does a comparison, and it crosses out one. Okay? So you only have n things to cross out, and each comparison takes, 1 unit of time. So every time you do a comparison, you cross out one. So you're only going to do n comparisons when you do the merge. Okay? Order n. Two subproblems of size n over 2. Those were the subroutine calls. There's our recurrence, right? Two subproblems of size n over 2 plus order n for the split and merge. Okay? Okay, a equals 2, b equals 2, d equals 1. Log base 2 of 2 equals 1. T of n equals O of n log n. Okay? So there's your sorting algorithm. Okay? So there's so 61A has this really, if you look at their lecture slides, which I can post a link to, it has this use of a comb. It's one of these sorts of things where you think about the data structures. Somehow it's a little bit nicer to do it in different ways. So it's very cute what they do in 61B. I'll post the slides and tell you what they are. Okay, so the book also has a different way of doing merge sort. The observation is the following: you don't do anything on the way down. Like you're just splitting the array, right? You're not comparing elements. You know nothing about the elements. Here's some for you, and here's some for you. I get my stack of finals, and I give half to one TA and a half to the other TA. Nothing. I didn't even look at them, right? And then he sorts them, and then when he comes back, then I have to do my work. I do my comparison then. Okay? So you do your comparison on the way up. So the book has this very clever way of, let's just take our array and take two adjacent items and compare them, more or less. Okay, now you have adjacent lists, essentially, that are sorted. Now you take two adjacent lists, and then you merge them. So they give you a clever data structure way to go bottom up. So some of these can be better than others, depending on the behavior of your machine. But for all of these methods, they're still O of n log n. Okay, so there's this cleverness, which is cool, this cleverness, which is cool. None get you past the O of n log n. Okay? Why? Why did none get you past the O of log? Because you can't get past the n log n. Okay? You really any comparison based, if what you do with elements is you just compare two elements, you can't do better than n log n. It takes at least n log n time comparisons to do it. Okay? So let me show you why. Okay, so this is very cool, but it might make you nervous. So just calm down. We don't go that deep into proving you can't do something, right? So this is what Christos said. Can you, how fast is it? Is it correct? How fast is it? Can you do better? In this answer, we can actually prove you can't do better for these types of algorithms. Okay? Mostly we're like, okay, well, maybe you could do better, but we don't know how. Or it's a leading question, we show you a better way. Okay, here we could actually show you can't do better. Okay, so this is very rare in this class, but I just wanted to show you an example. So you have an input A1 through AN. These are your elements that are input. Okay, a possible output is A8 may have been the lowest one, A15 may have been the next one, and all the rest may have been in the middle, and the middle one may have been last, right? What is this? It's kind of a permutation of the original elements. Okay? So we could represent this output as 8, 15, whatever. Okay? So we represent the output as a permutation of the original, what we put in. Okay, so the output, you're given 1 through n, and your output those same elements in a different order. That's a permutation. So we just write out it as a permutation of the original numbers. Okay? So the output is really just saying, oh, number one went to position 8. Number 8 went to position 1, right? Okay, so this is, so how many permutations are there of n? How many outputs are there? It's also, how many permutations is also the same number of outputs of your algorithm. It's the same number of different behaviors of your algorithm, right? The number, you better behave differently if you have a different output. If you don't behave different, if nothing changes, if you don't do anything differently, the same result happens, right? Okay, so how many outputs is n factorial? So each comparison has, let's just say there's no ties. Each comparison has 2 possible things, either greater than or less than. Now these algorithms, they always say, if A is greater than A prime, do this. Otherwise, do that. That's what they do. That's all they're allowed to do. Otherwise, if A is greater than B, it always goes down this branch. Okay? So for each one of these things, it can only branch in 2 directions for each comparison. Meaningfully. I mean, it may do something else, but it's not meaningful. So at the beginning, your current output is n factorial. At any point, once you do a comparison, you can split the number of possible outputs into 2 sets. Once you do a comparison, you can say, well, okay, all these outputs I know aren't good anymore. Okay? Or if the comparison went the other way, you say these outputs aren't good anymore. So at most, you can divide the set of possible outputs. Given one comparison, you can divide the set of possible outputs by 2. So the larger set of possible outputs contains at least 1/2 the previous possible number of outputs. Okay? Okay. So to get down to 1 possible output, right? The algorithm needs to output 1 output. It needs to say, okay, item 5, item 7, item 8. It just outputs the whole sorted order. That is a permutation. It has to be the right one. It can't output any one from a set, right? These are all different. So you need log of the total number of original outputs comparisons, right? Because each comparison can only divide the number of possible outputs by 2. So you need log of this number comparisons to get to 1. Okay? Now, n factorial is greater than this. This is just some Stirling's formula from Stirling. So now if you take the log of this, log of n factorial is more or less omega of log of n to the n, which is omega of n log n. I mean, this looks so harmless. It's like log of n, that's not so bad. But the factorial is bad. It's really bad. Okay? So the number of comparisons has to be n log n. Okay? Okay, so now, So it says those algorithms are optimal. So all this data structure tweaking, it's cool, it's interesting. It may make it work better in a constant factor, but it's not going to do what this faster multiplication algorithm did compared to the naive one. It won't give you this asymptotic improvement. Okay, but there are faster sorting algorithms, and the key is they look at the bits. Here, all you're allowed to do with the numbers is compare them. When you do radix sort, you actually say, I could do that with the finals as well. I could take my stack of finals. I could first put all the A's in a stack, and then all the B's in the stack, and all the C's in the stack. That's a different algorithm. I'm not just taking two papers and comparing it and saying, Rao is lower than Papadimitriou, higher, lower, okay. Right, I can look at the letter R and look at the letter C. That's what you do in radix sort. They're just not comparing, they're just doing something more than just comparing the keys. So that's why in those cases you can maybe do better. But you have to change the nature of the algorithm. You're not just doing comparisons. Okay? Okay. So, so let me motivate this problem for Christos, and then I'll let you go. Or it's kind of cool, the motivation, so I'll let you do this. So next time we're going to work on median. And this is, so median is you have these n items. Okay, yes. Okay, so I will let you go by 12:30, but please be considerate and don't shuffle anything until I'll let you go. Thank you. Okay, so it just makes everybody nervous and stop listening. And so median is a value, v, where n over 2 elements are less than v. That's just the way we're going to define it. Exactly n over 2 are less than v, and n over 2 are bigger than v. Let's just assume n is odd, because otherwise just the language is hard. Okay? Okay, why do you want to do median versus average? Well, let's think. The average household income in 2004 was $70,000. Right? What one tells you more about the typical person? Somebody in the middle of the population is making $43,000, but the average income is $70,000. So which one is more indicative of what is typical? Yeah, I would think median, right? So that's maybe some people think average, but maybe it seems at least median is interesting. It's interesting. It's so different, right? So this is why you may want to do median. Okay. So now, one could ask sociological reasons as to why this is different, but we won't really go there. Okay. Was that? Oh. How did that appear there? Okay, so, but clearly this is what something is happening. It's not my domain to discuss that. So, why use average? Why do people use average so often? Okay. Well, how do you find the average? Everybody know how to find the average? You add them up and divide by the number. Dang, that's easy. Right? And we could even analyze its running time. O of n. That rocks, right? It's pretty easy to compute. Computing the median. How do you do that? Okay, you can sort. And then output the n over 2 plus 1th element. But already that's worse, right? It's analog n. And you have to be clever to sort, right? If you do it naively, there's a problem. So I'll let Christos finish.